Hello. I'm going to chat a little bit about some testing I've been doing for EMC pre-compliance. This video is about conducted common mode disturbances on telecommunication ports. This is a test that can be run in a home or in a small lab, and you can get very repeatable results that will match a certified compliance laboratory. I am using my Rigol DSA 815 spectrum analyzer. I have the settings set to dB microvolts, top scale of 100 dB microvolts. Our frequencies of interest are 150 kilohertz to 30 megahertz. I actually have it set to 35 megahertz so that I can see a 30 megahertz signal here that I wanted to show you. So what I've done to facilitate some of this testing is I've made a little jig. This jig has a 5 volt input, a 10 megahertz TTL oscillator that is connected to a mag jack. So the signal is running through the transformer and goes down to a single pair on this Cat5 cable, and this is going to be my common mode source. This is a Teseq ISN for Cat5, Cat6 cables. These devices are fairly expensive. This may be close to $1,500 to $2,000, so similar in price to the spectrum analyzer. Fortunately, you can make one of these. In the EN 55022 standard, they publish what the inside, or the typical, what the inside of these ISNs look like. There is typically going to be two common mode inductors, here and here. All four pairs come in through this side. There's a ninth winding here, which is the pickup, which comes out to the BNC. So this is the DUT or EUT side. This is the Impedance Stabilization Network side of these associated equipment. So another toroid inductor with all four pairs wrapped around. And that's the basics of what these things look like in the inside. I'm going to hook up my signal source. Note that I have a transient limiter connected between the ISN and my spectrum analyzer, and this transient limiter also has a 10 dB attenuation, which I have factored into the setups of this device. I'm going to turn on my unit here. I'm plugged into the wrong side. I'll show you what that does later on. Okay, so here we go. So I've got my 10 megahertz fundamental, and then I've got a 20 megahertz and a 30 megahertz signal here, as you can see. This reading is approximately 100 dB microvolts. I can freeze this. Okay, I'm going to capture that waveform. I'll freeze it, come into a second trace. I'll reverse this, and capture the signal again. So here we can see that there is a pretty amazing rejection of, or showing the directionality of the ISN. We are 100 dB microvolts, looking at it, I'll call it the forward direction, and the reverse direction, we are maybe 65 dB microvolts, so 35 dB difference. Let me freeze that. So another thing I can do now, I've got these references set up, and I can hook up a camera. I'm going to hook up an IP camera. This is the network that's in my lab. This has a PoE injector. That will hook up to the associated equipment port. Here's the camera. Turn off the power supply so my 10 megahertz test signal is not running around. Okay, hooked up the camera. I'm going to wait for this to light up, saying that it's powered. Okay, it's powered. I can also hear the camera. It has a shutter that opens and closes. I'll wait for this to start blinking, meaning that we've got communication and data flowing. Okay, so there's some data. And I will capture that. And let's freeze it. Okay, so we can see that there is some noise that's being generated here from the IP camera. The EN 55022 standard specifies that the average level should be below 64 dB microvolts from that roughly that 150 kilohertz to 30 megahertz. It actually allows a little bit more at the low end response, but 64 is a good number for right now. This is our 65. So the 70, 60, 65. And so we can roughly see that this system should, it's roughly in the ballpark to be below that 64 microvolts. I'm going to clear all of these traces. I'm going to capture that again. Freeze it. Go to another trace. And then we'll flip this around. I'll wait for it to power up. We're waiting for this LED to turn green and then start blinking. Okay, the camera is powered. Any day, there we go. Now it's communicating. I'll do another capture. Oh, that's interesting, some noise that we just caught here. Let me try that again. Okay, so we can see that running in this direction that there is it's quieter. So there's more noise contribution from the camera than there is from the associated equipment. I'm going to disconnect the camera. Go back to our signal source. Clear all the traces. Go back to our trace 1. Capture the data. Freeze. Okay, so this is our reference ISN made by Teseq. So I mentioned I made my own version, and This is a 2-layer circuit board, total ground plane on this side. Here are my 2 inductors. I have all 4 pairs of Ethernet cable wrapped around this inductor to meet the standard specification, which is, I believe it's around 3 millihenries. There's a 9th wire that is the same ratio as the same number of wraps, and this is the pickup, which is fed to this BNC. This is the 2nd common mode inductor, which is the associated equipment side. I went with these DB25 connectors because I wanted to have adapters that I can plug in like so. So for either a RJ45 or maybe a RJ11, a 4-position or a 6-position, so it allows me to keep this circuit board the same and just make these inexpensive little adapters. So I put all of this in a box I bought on eBay. It's a metal aluminum box, and it turned out pretty slick. I'll hook up this, put in my 10 megahertz test signal, and go to another trace for comparison. Max hold. Okay, and let's freeze it. This is some noise that I'm picking up down here. We can see that the fundamental, the 10 megahertz and the 20 megahertz are nearly identical. We can see that my 30 megahertz is a little off right now. I think it's a little less than 10 dB difference at 30 megahertz. When I've looked at the frequency response, it's almost identical up to just a few megahertz short of 30. So if I were to put the IP camera through here again, wait for that to power up. Wait for it to start blinking. There we go. And capture some data. You see that I get similar results with my DIY version, and that's pretty much what I wanted to show. Basically, I have a pretty high confidence level that if I were to take this same setup and go up to our certified lab and pay the big bucks to do the testing there,